Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Maxwell-Boltzmann distribution law. Let's begin. Maxwell-Boltzmann distribution law basically describes how energy is distributed among the particles or molecules or atoms. Let us consider a vessel in that of vessel there are n number of molecules, n the total number of molecules inside the vessel and that vessel have volume V. V is the volume of that vessel. N number of molecules are enclosed within that of an isolated vessel. That vessel have volume V. Here we take the gas molecules, and that gas are nothing but ideal gas in equilibrium state. Here we take an ideal gas, that ideal gas in its equilibrium state. These gas molecules are in random motions with different velocities, hence they possess different momentum and energy. During their random motions, the molecules are colliding with one another and with walls of that vessel. Therefore, their momentum and energies are continuously changing. Since the gas is thermally isolated, therefore, the total energy of that particular system is constant. Let us say U be the total energy of that system and which is constant. Now, the total energy of the ideal gas that enclosed within that of volume V, now divided into the individual particles, individual gas molecules. Let we consider the total energy of that ideal gas is divided into k intervals. K intervals. Here interval number 1, means n number of molecules are to be distributed in k number of compartments. Let me consider this is the compartment 1, this is the compartment 1. In that of compartment, the energy, let U1, that is the mean energies of the molecules inside that of compartment 1. Let this one be the compartment number 2, and here the energy, let U2, that is the compartment number 3, let the mean energy, that is U3. Like this is continued. So at k compartment, the mean energy of the molecules present in that of kth compartment, let U of k, right. Here U1, U2, U3 up to Uk, these are the mean energies of intervals, or we call it as compartments, intervals or compartments named as 1, 2, 3 up to k respectively. In compartment number 1, it has the mean energy U1, compartment number 2, it has the mean energy U2, like this. Again, let N1 is the number of molecules in that of compartment 1. That number of molecules have mean energies U1. Similarly, in compartment 2, the number of molecules N2, compartment 3, the number of molecules N3, up to at that compartment number k, the molecules Nk. Here N1, N2, N3 up to Nk, these are the number of molecules of intervals, or we can say that is the compartments named as 1, 2, 3 up to k respectively. Next, let these compartments, or we call it as intervals, are further divided into large number of elementary cells, and each elementary cell has equal size. So, let the compartment number 1 is divided into small gi, sorry g1 number of such elementary cells. Next, compartment 2 divided into g2 number of elementary cells, like that of compartment number 3 and up to compartment number k. Okay. I clarify it. By taking the red box here. Write as Gi, sorry G1, G2, G3 up to Gk. These are the number of elementary cells of compartments or intervals. These are named as 1, 2, 3 up to k respectively. Here we taken k number of compartments, and each compartment have the mean energy interval as u1, u2, u3 like uk. Next, each compartment the number of particles like n1, n2, n3 up to nk, and each compartment is divided into a number of elementary cells. Let compartment 1 as G1 number of elementary cells, compartment 2 G2 up to Gk. Taking a mathematical analysis, let we prefer a compartment number which is called ith compartment. Ith compartment. In ith compartment, it has the mean energy ui, number of particles in that of ith compartment let ni, and it is divided into a large number of elementary cells that is given as gi. Okay. Let us consider Ni are number of molecules and Gi are the number of cells having mean energy ui of ith interval or compartment. Okay. Now we can calculate what be the thermodynamic probability of most probable macro state. First we have to understand what is most probable macro state. Most probable macro state is that macro state in which large number of microstates are present. That is, the highest number of microstates are present in that particular macro state, then this type of macro state we called most probable macro state, and that most probable macro state we achieved in case of equilibrium condition. Therefore, we take an ideal gas in equilibrium state. Now, we know that the thermodynamic probability of most probable macro state is given by thermodynamic probability W is equal to that thermodynamic probability for most probable macro state. Most probable macro state we achieved when that system is in equilibrium state, and it is the highest number of micro state present in that of macro state is considered as most probable macro state. Here the thermodynamic probability is calculated. Look here, in that of compartment 1, it is divided into G1 number of such elementary cells and with N1 number of molecules. So the arrangements like G1 to the power N1, similarly in second G2 to the power N2, third G3 to the power N3 up to Gk to the power Nk. Within that Gi to the power Ni divided by, as we taken the probability, so the number of particles in compartment 1 as n1 factorial, next n2 factorial, next n3 factorial up to ni factorial up to nk factorial, and the total number of particles, n is the total number of particles, it is n factorial. Now in form of notation we can write that thermodynamic probability W is equal to, that is n factorial into, we use a sign which is called multipliers. In case of addition 1, 2, 3 up to n, we use summation. Similarly for multiplication we use multiplier, that multiplier from I is equal to 1 to k Gi to the power Ni divided by Ni factorial. That entire terms are now written in terms of multipliers. Taking a logarithm on both sides, taking logarithms both sides, we obtain ln W is equal to, two terms are multiplied, ln AB is equal to ln A plus ln B. Here ln n factorial plus ln of that entire term. Now this is ln A by B, ln A minus ln B. So that a term is written as, it is changed to summation I is equal to 1 to k Ni ln Gi ln A to the power n, that is n into ln A, that is the formula of logarithm. Next minus summation over I is equal to 1 to k ln ni factorial. So first ln ab ln a plus ln b, next ln of a by b ln a minus ln b, ln of a to the power n n ln n. These logarithm formulas are used to evaluate such term. Next, look here, since n and ni are very large numbers, hence its logarithm can be evaluated by using a formula which is called Streling's equation. Equation number 1. Here assuming that n and ni are very large numbers, hence we can use Streling's equation to calculate logarithm of that factorial terms. Therefore, that equation now written as ln w is equal to ln n factorial. Now we use Streling's equation as it is n ln n minus n, ln n factorial n ln n minus n, plus summation over I from 1 to k ni ln gi minus again ln ni factorial. We use Streling's equation I from 1 to k ni ln ni minus ni, okay, is equal to n ln n minus n plus summation over I from 1 to k ni ln gi. Now separating these two terms, minus summation over I from 1 to k ni ln ni minus minus plus summation over I from 1 to k ni. Now summation over ni from I to k, that is the total number of molecules, that is n ln n minus n plus summation over I from 1 to k ni ln gi minus summation over I from 1 to k ni ln ni plus n, summation over ni from I to k, that is the total number of molecules. Here plus n minus n cancelled out, we obtain n ln n plus summation over I from 1 to k ni ln gi minus summation over I from 1 to k ni ln ni, which is equal to ln w. And equation number 2. Now we can differentiate it. In that of differentiation, here N and Gi, these are the constants. N is the total number of molecules, Gi, that is the number of elementary cells of ith particle. Since N and Gi are constants, so the differentiation results. Now differentiating both sides of equation number 2, we get the differentiation as d of ln w is equal to n ln n as entirely constant, result as 0, plus summation over I from 1 to k, here Gi as constant, Ni as variable, so d Ni ln Gi minus, here two terms, its differentiation of first term, second as constant, next differentiation of second term, first term as constant, I is equal to 1 to k d Ni ln Ni minus summation over I from 1 to k Ni, differentiation of ln Ni as 1 by Ni into dNi is equal to summation over I from 1 to k dNi into ln Gi minus summation over I from 1 to k dNi into ln Ni, here Ni cancel out, that is summation over I from 1 to k dNi, summation over I from 1 to k to dNi. How the number of ith particle can be changed? It is a constant term, so it results as 0 is equal to summation over I from 1 to k dNi ln Gi minus summation from I to k dNi into ln Ni minus 0, which is equal to summation over I from 1 to k dNi ln Gi minus summation over 1 to k dNi into ln Ni. Or d ln w is equal to, in these two terms dNi as common, so it is summation over I from 1 to k taking dNi as common, so dNi in that of bracket it is ln Gi minus ln Ni, that is equation number 3. But we consider the thermodynamic probability in most probable macro state. So we write for most probable macro state, the thermodynamic probability is maximum. The thermodynamic probability is maximum, that is W is equal to W max, hence its differentiation result as dw will be 0, therefore d ln w, since it is too high, its differentiation results as 0. So equation 3 can be written as for equation number 3 can be written as zero is equal to summation over I from 1 to k, here ln gi minus ln ni into dni, equation number 4. Next, we can apply that condition for most probable macro state for total number of molecules and total number of energy. Now applying conditions that total number of molecules n and total energy U of the system that is constant. We taken total number of molecules and total energy as constant. So that is total number of molecules n is written as, it is summation over I from 1 to k ni, which is a constant term. So its differentiation dn will be 0. Let a equation number as a. Okay, that term dn is equal to that much as 0, which is summation over I from 1 to k, that is d ni, therefore simply d ni is equal to 0, that is equation number a. And total amount of energy u summation over I from 1 to k ui, that is a constant, therefore its differentiation du is equal to summation over I from 1 to k dui is equal to zero. Okay, total energy is the energy of ith compartment, that is the mean energy, into the number of particles present in that of ith compartment, that is ni. So it's dni into ui, which results 0, or summation over I from 1 to k ui into dni is equal to 0. That equation number B. We can multiply a constant to that equation number A, another constant to equation number B, and subtract these two equations from one another. Now multiplying equation A by alpha and equation B by beta and subtract them from equation number, here we taken d ln a, d ln w as that much, that equation number 3, let 3 or 4, what you can say, equation number 3 we get. So ln w, subtracting that equation multiplied by a constant alpha, summation over I from 1 to k constant alpha into dni minus summation over 1 to k a constant beta ui dni is equal to 0, or ln w as summation over I from 1 to k ln gi minus ln ni dni this is the value of ln w as I write in that equation number 3, minus summation over I from 1 to k alpha into dni minus summation I from 1 to k beta ui dni is equal to 0. In all these three terms dni as common, it is summation from I 1 to k ln gi minus ln ni minus alpha minus beta ui whole into dni is equal to 0. As we say, dni are the independent variables, so that equation can be valid only if the bracket quantity will be 0. The equation number 5, as dni are independent variables, hence the equation number 5 will be valid only if the quantity inside the bracket is 0, that is ln gi minus ln ni minus alpha minus beta ui is equal to 0. Therefore, ln gi divided by Ni ln A minus ln B, ln A by B minus alpha minus beta ui is equal to 0, or ln gi divided by ni is equal to alpha plus beta ui, or gi divided by ni is equal to e to the power alpha plus beta ui, or ni divided by gi is equal to 1 divided by e to the power alpha plus beta ui, or ni is equal to gi multiplied divided by e to the power alpha plus beta into ui, or ni is equal to gi divided by e to the power a plus b, e to the power a into e to the power b, e to the power alpha into e to the power beta into ui. That is the required expression, which is called Maxwell's law of energy distribution. This is called Maxwell-Boltzmann's law of energy distribution. Maxwell-Boltzmann law of energy distribution. That is the fundamental law. When we put the values of the constants alpha, beta and gi, then completely we derive the expression for the how the energies are distributed among the particles. So, with the help of this video lecture, we understand the concept of Maxwell-Boltzmann distribution law, thermodynamic probability of most probable macrostate, taking logarithm on both sides, and using Stirling's equation, we obtain d ln w. For most probable macrostate, it will be 0. Applying that same condition, most probable macrostate for total number of molecules and total energy, multiplying alpha, equation number A, multiplying beta, equation number B, alpha beta are constants, and then subtracting it to that of equation number 3, as the differentiation results 0. So, all are subtracted from that ln w. Under simplification, we obtain Ni is equal to that much, which is called Maxwell-Boltzmann law of energy distribution. So, with this useful and informative notes, let me wind up the session. Thank you.